Hello, everyone. I know we finished talking about gravity and we're going to move on to simple harmonic motion, just a brief introduction to it. But I thought I would talk about transferring orbits because it provides a nice wrap up to what we've learned so far in our discussion with gravity. So we learned by applying Newton's second law of motion, F equals ma, we put in the centripetal acceleration, we put in the gravitational force, and we found that your velocity in orbit depends upon big G, the mass of the object, and the distance you are from that object, all under a square root. The next thing we learned was Kepler's laws. And from Kepler, we learned that this relationship tells us that the closer you are to the massive body, the faster you will be going. Okay. So what we'd like to get ourselves in this situation to do is change our orbit to go from, let's get our massive body in here, I'll get it circular in a second, to go from an inner orbit to someplace farther out. And the way that is done is by adding some velocity to the system. So our goal is to move the satellite or whatever from its closer radius to a stable outer radius. So in effect, what we're trying to do is we're trying to build this ellipse for the satellite, for the box. So initially, we know that the inner velocity is equal to the square root of gm over d. Gm over d. Then that inner velocity is now serving the role, so let me get down to this. D is now equal to the inner, for our ellipse. So from our ellipse, we get that the velocity point 2, so this will be 1, this will be 2. The velocity of point 2 is equal to whatever our R1 is, which is going to be d, and wherever we end up at R2, and that's times velocity 1, which is just the velocity of the inner. And then, okay, so let's calculate the speed at V2. The velocity at speed 2 is given by d inner over the radius of 2. And our v initial was square root of g over m d, still the inner. So let's just, for simplicity's sake, square everything. So we're going to go v squared and all of this squared. I'm going to get v2 squared is equal to di squared radius at 2 squared. And that's going to equal gm over di. So we will cancel out one of the di's when we do this. But the other thing we've done is, let's see, we can replace the velocity. No, I don't think that's the best way to go. Let's do something just entirely different, and I'll let you know here why. So rather than squaring all of this, let's throw some numbers in. Oops. So a reasonable orbit for a satellite would be, let's say 200 kilometers. So 200 times 10 to the 3 meters. If we're dealing with the Earth, then I need to add the radius of the Earth, or 6.4 times 10 to the 6 meters. Radius we're heading to, we don't know yet, so I'll put that down. Then we're going to wind up with the square root of big G, mass of the Earth, and then let's see, 10 to the 5th, that'll make that 6.6 times 10 to the 6 meters as what D is actually equal to. So this will be our velocity when we get to point 2, wherever point 2 is. So let's pick a value for point 2. Let's set that value equal to, if we went from 200, let's say that we go to, how about something easy like 600 kilometers for R2. Oops, and forgot the Earth. Pesky Earth is always coming in to get you. Okay. So this tells me that my velocity at this new location is going to be 6 times 10 to the 6 meters divided by 6.4 plus 600, 700, so 70 times 10 to the 6 meters. And then we're left with square root g mass of the Earth all over 6 times 6 times 10 to the 6 meters. Okay. There's a little issue, though. We know what velocity 2 should be. In a circular orbit, it should equal this. So, this is its elliptical speed. And for it to go back into a circular orbit, velocity 2 has to equal square root gravity mass of the Earth, now divided by 7.0 times 10 to the 6th. Okay. If we... So here's the question I'm going to leave you with. What's this velocity? And what's this velocity numerically? Plug the values in and figure them out. And I'll give you a strange hint. If in our elliptical orbit we were to say put some work in there, apply a thrust, when we reach the outermost point, we fire our engines in the same direction. See if you can figure out why that is the case based on these two speeds.